So good morning, everyone. Thanks for joining for this third day of the meeting, which will be on tutorials. So we have Francesc giving a tutorial on Btune this morning, and also John talking about data services in the afternoon. So I'd just like to say a few organizational things. First of all, unfortunately, I need to leave early for a technical advisory committee thing. So I'll be sneaking out shortly after the start of the session, and Gert will be chairing the rest of the day. So I'd like to take the chance to say, thanks for you all for coming, and particularly to everyone who's contributed to the talks and discussion. As a few last organizational things, there will be coffee breaks mid-morning and after lunch, but not in the afternoon since it's finishing up a little earlier. So just so you know. And also we have a Petra tour running today at 3 o'clock. So that'll be running from the auditorium. It's a small number of people, so if anyone at the last minute wanted to join, I don't think that would be a problem. Okay, so thanks. I'll now hand over to Francesc so you can share your screen, and I'll get the Zoom set up on our side.
Thank you, David. Let me share my screen. Okay, so everyone
okay, yeah, that looks good from our side, thanks.
Excellent. Okay, so good morning, everybody, and welcome to the tutorial on Btune. As you know, Btune is a way to find the best codecs and filters for Blosc2. Today with me, I will have Marta Iborra, which has been developing Btune for Blosc2 for almost a year right now. So she's the in-house expert. So she will provide some support during the tutorial. And then I will introduce you also to Ivan Vilata. Ivan, can switch on your video so that people can see you. Okay. Well, he's relatively newcomer into the Blosc team, and he has been working on the implementation of the optimized path for Blosc2 in ASDF5 for bytetables. And he will be here mainly for learning, but also for giving a hand in case some of you have some problems with the setup. Okay, good. So having said that, just a brief reminder of for those of you that didn't attend my talk on Tuesday. So Btune can fine-tune the different parameters for the underlying Blosc2 storage to perform as best as possible. And by as best as possible, that means with some trade-off between compression ratio and the speed. We will see that how that it works later. And also, it can be trained as well in order to find the best codec and filter using deep learning techniques. So the requirements for the tutorial are you should have a laptop or a remote machine, should work well as you prefer. The operating systems supported for these tutorials are Linux, Mac OS, and Windows, but only via WSL. So please install it prior to the tutorial, and instructions to install it are there. Is there anybody in the room that has a Windows and doesn't have a WSL? Everyone is there? Okay.
Nobody. Yeah. So
excellent.
Good. Excellent.
Then it is recommended to have like a PyEnv, Conda, Mamba environment with a Python 3.10 or 3.11 installed. These are the minimum Python versions. And for those of you that are physically in the room, my advice is for you to do groups of three or I don't know, maybe 2 or 3 people, because in my experience, this is how it works best for teaching. So people can exchange opinions and experiences. So I will give you like 5 minutes or a few minutes in order to regroup and for doing the tutorial. By the way, how many people is physically in the room?
Let me see. 1, 2, 3, 4, 5, 6, 7, 8. David is leaving right now. Yeah.
Okay.
8.
Good. And then online we have like 4 or 5 more. Good. Excellent. So yeah, so take your time for grouping. Of course, this is an advice. You are not, if you prefer to be alone, it's up to you. But
Oh, the local count just increased by 3 with Andy, Thomas, and Jerome's arrival.
that's great. They can form a group if they want. Gert, as soon as you see people has already grouped, just tell me and I will continue.
Okay, I think we have a few. Yeah, we have one group of 3. Otherwise, we have soloists.
Okay, as you prefer. Good, excellent. So today, as you know, I am going to describe the different tiers of support for Btune. First of all, we are going to exercise the genetic one, which is about testing the different combinations of codecs and filters by brute force. Then there is the train mode, where the Blosc team train datasets for you. And this will give normally much better and accurate predictions for all the chunks that you are compressing. And then we will see how to do a full train on your own datasets if you want to. So without further ado, for the tutorial, just follow the instructions here. I am going to copy that to the chat. Oops, sorry. Okay, where is the chat? Chat is here. Okay. So everyone, it's in the same page, in the instructions for the tutorial now. Okay, good. So First of all, we will need to clone the repository. So I have set up a Btune tutorial repository. So just do a git clone the repository. And after that, just check that you have a Python that is 3.10 or 3.11. In case you don't have them, and for example, if you have Conda, you can easily create an environment with 3.11 this way. This is going to be very fast. After creating the environment, you need to activate it. For this, I'm going to use Python 3.11, but Python 3.10 should work equally well. And now let's install the Btune plugin. I am going to do the steps on my own, and you can follow me. I will increase the font size for that. Can you read my screen? Okay. Okay, so the first step is to install the actual Btune. So Btune, currently it's distributed as a dynamic plugin for Blosc2, and it is installed like the regular dynamic plugins. So it's just a matter of installing Blosc2 Btune, and then -u is for doing updates. Okay. In general, you should not need that, but just in case somebody already have a previous version. Okay. Now we have the plugin installed for Blosc2, and we will start doing genetic tuning now. So for doing that, in order to use Btune, there is an environment variable that drives the process. So whenever you set this Btune trade-off environment variable, then Btune is activated automatically, right? And in addition, you can also use Btune perf mode in order to optimize or to tell Btune to optimize the compression, or achieve a balance between the two by setting it to the strings comp, the comp, or balanced, respectively. And then if you want to see a trace of what is going on, how Btune is trying the different combinations, you activate this Btune trace environment variable. Okay. So with that, let's go to the inference directory and type this one. By the way, everyone is keeping with me. Everyone, anybody has problems? In case you have problems, just use the chat for the Zoom, and either Marta or Ivan can help you in fixing things.
All good here.
Excellent. So let's go to the inference directory. And then let's copy that. So what we are doing here is to set the Btune trace to see what Btune is doing, activating the trade-off, and we are selecting a trade-off of 0.5. So trade-off can take a value between 0 and 1. A value of 0 means that it tries to optimize for speed, for compression speed. And a trade-off of 1 means that it tries to optimize for compression ratio. And in the middle, you can have any floating point number that you want. And then there is this variable, which is called Btune perf mode, where you specify if you want to compress to optimize the compression speed, the compression or the compression speed, or if you put that to balance, it's going to use a balanced prediction, or a balance is trying to come up with a balanced outcome that behaves well in both modes. It's like a trade-off between compression and decompression. Okay, and then this is the randint.py. So let's, before running that, let's see what's there. So this is the script. Essentially, what is done, what it is doing without the flag -t, is that it's going to create an array of random integers between 0 and 2000. In order, and we have this, we put this limit because we want the result to be compressible somehow, right? Because if we don't put a higher value, we get completely random integers, and we don't get any compression ratio. So there is not much point in optimizing things for compression if our dataset doesn't compress. So with this setup, this is typical. This can compress up to 4.5x. Okay, so this is a good way to do that. And then this is the way for Blosc2 to create the array on disk. So Btune right now, it only works on Blosc2 arrays, but I mean, whenever you use the Blosc2, for example, in HDF5, in our forthcoming version of PyTables, it will be possible to do that, for example. You can use, whenever Blosc2 is used, the optimizations will apply as well to that. But for the time being, we are going to use native Blosc2 arrays. Okay, so this is what it's doing. Now let's execute that. Okay, so this is the string from the script, from the randint script, and here it is Btune in action. Okay, so it is stating the version of Btune, the performance mode, the compression trade-off that we are using. Bandwidth is important because Btune also accounts for the time it takes to transfer the data from disk or from memory or from the even from the network into the local computer. And by default, is using a bandwidth of 20 gigabytes per second, which is typically the size or the speed for memory, right? So for the examples that we are doing, the datasets normally fit in the operating system file system cache, and normally we are going to optimize for the memory cache, right? So this is why by default, the bandwidth is 20 gigabytes per second. But you can fine tune that and select for example, if your disk is only able to retrieve at 2 gigabytes per second, you can reduce that to 2. Btune will automatically take this speed for media transfer into account. And there are different things. So these are different parameters for the state machine. So let me show you how the state machine works. I already shown you before. So this is the state machine of Btune, and there are different states where in this first state the codec and filter are changed, and then there is one can change different shuffle size or threads or compression level. So there are, I mean, as soon there is a convergence, so when the score doesn't improve anymore, the state changes to the next state, to the next state. Okay, so it's a typical state machine, and we have different soft readaptations, different loops that loops over this stage, or hard readaptation. That means it is looping on this state again. So let me show you how those. So here, for example, it is testing different codecs, okay, in turn, and whenever the score is converging, it passes to the next state. So this is how this genetic algorithm works. Okay, so let's go back to our output and try to interpret that. Everyone is getting these results? Anyone has problems in getting that?
No, all good to you.
Excellent. Good. So here we have the different columns. So here we are seeing the codec that is being tried. Then the filter 0 means no filter, 1 is shuffle, 2 is bit shuffle, and then there is more shuffle that I am going to introduce later on. This split means something that Blosc support, and that means that whenever you use shuffle, you know that the most significant byte and the less significant bytes are grouped together, right? So for some reason, the codecs or the compression libraries sometimes work best when they compress only on these groups that are being tied together, and sometimes they work best when it compresses all the different bytes, all the different groups in one row, okay, in one attempt. So this means that split is activated, and 0 means a split is deactivated, and this has a good a noticeable effect in compression ratio. Here is the block size. Whenever you see a 0, means that it is automatic. So normally Blosc2 chooses the block size automatically for you. And this is the compression level that is being used for every compressor. Here, the number of threads for compression, the number of threads for the compression, and here it is the score. So the score, this is like a mix between the time that it takes to compress or decompress the different chunks, and then also the time that it takes to transmit the data in compressed state from the core memory into the CPU caches, right? So this is normally the lower the score, the best is the result. So we were trying to get the lowest scores as possible. And here is the compression ratio that is being achieved for every chunk. So all these lines means that a chunk has been tried. And then this is the state for Btune. This is the state of readaptation. And in this column, it is shown if this score has been declared a winner or not. So a winner means a W means a winner, and the dash means that this combination didn't win. So here we can see that the winner in this case was this one that was reaching a compression ratio of 4.52x, which is pretty good. It's pretty close to the maximum, and that was using LZ4 in combination with bit shuffle, okay, because it's number 2, and with it in a split mode. It tried without the split mode, but the compression ratio was not as good. And yeah, and this is the score that it achieved in the compression ratio. And then we can see that finally this has been created, this file. So yeah, it is a small one because I didn't want to put too much information in the screen, but for training purposes we will create a bigger one, right? So yeah, we already have done our first use of Btune in genetic mode. Now it's a good time for questions. If you have some, please tell us.
Yeah, there's a question.
Mm-hmm.
Good morning, Francesc.
Good morning.
Kiefer speaking.
Mm-hmm.
I had a look at the small Python script, and it basically creates an array of random data. And then the fact that Btune is called and all that looks like black magic. And I prefer explicit than implicit. So
yeah, it is not black. Sorry. No, go ahead.
It raises a couple of questions. The first is that it's far from being obvious for anybody because it's implicit, and the second one is this mechanism of Btune is always around and can be activated by an environment variable, which looks pretty dangerous because if somebody doesn't know, you could trigger the Btune tuning and how to say, if it's set on a computer that is in production, it's likely to change completely the behavior of the program.
Okay, so let me explain. First of all, I mean, there is no black magic going on. So let me show you what's going on. So whenever there is this environment variable in your environment, Btune is automatically load dynamically. So it is a dynamic plugin, right? So in case you don't want to have any accident, for example, like loading Btune by default, you can always use an environment that doesn't have the plugin installed. If the plugin is not installed, the dynamic plugin is not installed, or the wheel is not installed, it will not enter in action, right? This is one thing, and also, yeah, I mean, we designed Btune to be tunable from the environment variables because we think is the best way to interact with it from the point of view of the user, right? But for example, if you want more control over the different parameters, we also have the possibility to use it from C, and from C you will be able to choose any different parameter by hand. So you can choose all the different parameters by using the C wrapper for Btune, right? We don't have that in Python because our understanding is that Python users normally doesn't want to delve into the details, and we thought that the best way for Python users would be to use these environment variables. But if you are interested in having better control from the Python side of the things, I mean, we can do that, right? The only thing is that doing that this way, you can you can turn any existing script that you have for handling your data. You can use it automatically without any further action, and you can use it that script for tuning via Btune. So, does it make sense for you?
Thanks for the answer.
So, for example, if we doesn't activate this Btune trade-off, we don't see any of the messages for Btune. It is completely deactivated. And then this is using only Blosc2, is the only dependency that they have. And if you are not setting this environment variable, this one, oh, sorry, this Btune trade-off, it will not be loaded dynamically. So you are safe, completely safe. Okay?
Hi, Francesc. Franz Pöschel talking here with another question following up on this.
Mm-hmm.
Do I understand it correctly if I have a rather big software stack that is for example, a simulation code, and I don't even know exactly the way how Blosc is internally implemented. But if I have in my development environment installed Blosc with the Btune plugin, I can then just use the environment variable to tune Blosc for that particular simulation without even knowing how the implementation works with somewhere down the software stack.
You are saying that in your environment you can use it. You can use Btune trade-off, or you cannot.
Well, that's a question. If I have a simulation where I know somewhere down the line it uses Blosc, and I can configure Blosc, but I don't know the exact implementation. So if I understand the idea of Btune correctly, then having this control via environment variables means that I just need to set the environment variables and then have Btune give me the best configuration for this particular simulation. Exactly.
That's the point. Whenever you have this environment variable, Btune enter into action. If you don't define that, Btune will never be in your way.
Okay.
Okay.
Clarifies things. Thank you.
Thank you. Good. So
there's another question here. Hold on.
Yeah, sure.
Yeah, to follow up, almost the same question. So let's say that the software that we want to tune, or that we turn into being tuned by enabling this environment variable, is something that writes to HTML5 in a chunked way. So the Blosc compressor is called many times on many chunks. Does it mean that it will start doing all the tuning on the first chunk and then later retune on the second chunk and so on?
Yeah, so in this mode, what is happening is that for every chunk, there is tuning is activated, right? So the first chunk, it is going to try this codec first. For the second chunk, this combination is going to be tried, right? And Btune has an internal state where it takes notes of the different scores for the different chunks. And when the training finish after, I don't know, it depends on the number of readaptations that you do, the hard or soft readaptations. Typically it finished between 10 and 100 chunks. And then the rest of the chunks, and then Btune is considered to be like trained in this mode, genetic mode. Later on, we will see how you can optimize that by using the training, the deep learning training. But after the training process, all the different chunks will be compressed with the winner combination. In this case.
So in your example, there was no loop, but you got chunks because you had a big array. Or...
Exactly.
Yeah, thank you.
Yeah. Okay.
Hi.
Yeah.
Hi, Francesc. Nicola from Alba speaking.
Hola, Nicola.
I wasn't sure why is the first line separate from the others. Is it because of the genetic algorithm? Do they correspond to rounds in the algorithm?
Sorry, say it again.
Why is the first line separate from the others?
Yeah, I think this is a bug. For some reason, for example, you see this duplication in the header. So probably we are duplicating that. It is a bug on the thing. We will take note of that.
Thanks.
But that's a good question.
Hi, Francesc. Jérôme again. If one imagines a processing pipeline like the one I presented today ago, where we read first some data, we perform some transformation and save the data. There will be two operations.
Reading and writing. Yeah.
This will trigger twice the Btune. Well, how is it managed? This, the fact that you do several within one application, you do several call to Blosc2.
Yeah, that's a good question. Actually, we didn't thought a lot about that. I mean,
so this requires at the end, well, because I have the feeling that this requires to write a specific application to be tuned or profiled. Well, you say that Python developers are not very keen on fiddling with the details, but at the end they still need to write a specific application to be able to profile it.
Yeah, yeah. I think I know what the answer. I remember now. So Btune only works for writing, right? It doesn't optimize anything in reading mode. I mean, it makes no sense to optimize for reading because data is already compressed. So Blosc2 only will have to decompress that, right? So whenever there is a performance mode for the compression, that means that we want to compress in order to ensure good decompression times.
But typically, if I save some data after processing them, I'd like, for example, to store the process data and the standard deviation of those results. So this will be two calls with two data sets or two arrays which have different
needs,
typical,
yes.
different meaning and different
right.
characteristic on the numerical point of view.
Right.
And so they are likely to compress in a completely different manner also.
Yes. So for this, yeah, I mean, the current way is to use the CAPI, but I understand the need. And yeah, probably what we can do is to provide a Python interface in order to be able to fine tune which trade-off wants or which performance mode you want for every data set that you are writing in the same script. Right now we are just optimizing for on the case that you're writing one single data set. But yeah, your point is taken, and we will think about it. I mean, the nice thing about the current implementation is that you don't need to instrument your Python code right now, right? You can specify your requirements right from the environment variables. But yeah, we will think about it and we'll try to come with a solution. Thank you.
Hi, Francesc, Thomas Vincent speaking. Just to make sure I fully understand, so like when you say it's try for different compression for each chunk, it's the small chunk inside Blosc, right? No,
it's the whole chunk. So Blosc has the notion of chunk and the block. So the block is the small chunk that you are saying inside of the chunk. So okay. Here we are. I mean, Btune can only optimize for whole chunks, which is. I mean, with Blosc2 doesn't support having a chunk, with different blocks inside, compressed with different parameters, with different codecs or different filters. This is not supported.
Yeah, okay, it makes sense because then you parallelize the same algorithm, I guess.
Exactly.
Okay.
Exactly.
Then the data here is split in chunks, and those chunks are split in blocks.
Yes.
Yeah. Okay.
Mm-hmm.
And second question was to make sure for the score, if I understand well, you take the time it took to compress.
Yeah.
Take the size of the data, multiply by, like, you get the time with the speed.
Yes.
And then you put the time to decompress, and that's the score, sort of.
Yes.
Okay, good.
Mm-hmm.
Makes sense.
Well, the time to decompress only is taken in account when you use the balance. I mean, when you are using the performance mode, which is compression, only the compression time is taken in account. When you use the compression performance mode, only the decompression time is taken in account. And when you use balance, that means that you are taking both at the same time.
Okay.
Mm-hmm.
Okay.
Okay.
Thanks. Any other questions here for now? No, I think we are good. And I think your colleagues answered the questions on the chat. Now our Zoom session here just died. I don't know what's going on.
Yeah, there is, I think it's Andy, probably he's using Windows, and we said that you need WSL, Andy, for trying that. Sorry about that. We are working on a native Windows plugin, but it is not, I mean, TensorFlow is such a big beast that it's not easy to generate binaries from TensorFlow for every platform. And right now, Windows is giving us a bit of headaches, but we are still working on it. Sorry about that. Okay, so let's continue with that. I just didn't mention that in this winner column, there are some times that you will see some S symbols here, characters, meaning that the chunk is special. So Blosc2 has this notion of special chunks, and special chunks are made of fully repeated values, right? So this works extremely well for sparse data. So whenever you have like a block which is made of zeros or any value that is repeated all the time, it is considered special. It is encoded in a very compact way, so it's very fast when decompressing it. And then in Btune, this is going to be marked as S because it makes no sense to optimize a special chunk. Okay. By the way, special blocks also exist for sparse data that can be multidimensional as well, and this also is a nice opportunity for compressing sparse data very efficiently inside Blosc2. Okay. Now let's continue. Now I will. I would like you to execute to exercise Btune on your own. I am suggesting here different performance mode, different trade-offs, and you should try to find different. I mean, I want you to look at the score and the compression ratio columns and take your own conclusions. So I will give you like 20 minutes for doing so, or maybe 15 minutes, and then we can have like a brief chat on your own conclusions and for answering some questions. Good.
Sounds good. Yeah, we have a little bit of a network issue here on this machine for some reason. I lost the.
Hey, I've got another question on installation,
Sure.
Because if I follow the README on the GitHub page, then the currently only supported or at least advertised installation method is via Python wheels, which is not necessarily the software stack that one is otherwise using. For example, on a cluster system, one might have a Blosc module somehow, or maybe Blosc is also installed manually in some kind of development environment. So how is the interplay between the Python wheel and some other generic form of Blosc installation, or is it possible to install it manually? Or if I install the Python wheel, would a HPC module find that wheel, or how does that work?
Yeah, I mean, we already in the Blosc team we put a lot of thought on trying to make things as smooth as possible from the user point of view. Our current approach is to use wheels because, in my opinion, wheels are a very neat way to distribute binary software. So wheels, Python wheels, maybe people think that they are only a way to distribute Python code, but actually it's much more powerful than that. And this is the demonstration. So Btune is mainly a C library, right? And we are just using a Python wheel in order to distribute it. As I said, in our opinion, Python is very well spread, so you can find Python in all the competing machines, in most of the competing machines or environments that you can think of. And pip is coming with Python as well. So I don't think, as it is a C library, the way that the dynamic plugin works is that it looks into the current environment for a package which is called Blosc Btune, and the Python is returning the path for the library, right? And that's a very easy way to even a C application can find that quite easily, because under the hood it is Blosc2 who is doing who is calling the dynamic plugin. Whether or not this is a good fit for your platform, we will be happy to discuss your situation in more detail and trying to come with a solution for you. Do you think that using Python wheels or wheels like this is going to create some problems in your environment?
I'm not necessarily saying that using Python wheels is the problem, because you're right that I can use them practically anywhere. But so what you're saying is that this does not imply that I need to change the rest of my software stack. But instead,
exactly.
If I have Blosc installed somehow and install the Python wheel, then they will find each other somehow.
Yeah, and then you can also play with Python path in case you want to install that in a different place. And with the Python path environment variable, you can direct Blosc applications to find where the plugin is installed, right?
Okay,
so
sounds good. Then thank
good.
you.
Okay. So as soon as people is getting some conclusions and answering questions there, I would appreciate if they can write their conclusions on the chat, so that others can see them and we can have a more productive discussion in 5 minutes or so. Also regarding the wheels question, I mean, wheels in my opinion, are very well implemented in that they support like really old operating systems. So yeah, I mean, I think the Python wheels have a lot of potential for being a nice distribution way to, as I said, not only for Python packages, but also for C packages. And we are using that for C packages as well. I have just sent a question in the chat so that people can start providing their own conclusions there. Okay, so yeah, the time has passed for the exercises. So yeah, let me show you my results, for example, for using performance mode decompression here. And this is the result. So in this case, we had a winner, which is the codec LZ4HC, which is a codec that exists in Blosc. That is the same codec than LZ4, but especially meant for achieving high compression ratio. So it takes much more to compress, but it's very, very fast for the compression, right? And in all the scenarios where the compression speed is important, this is a codec that you should always check for. And then the best filter for the compression speed is number 2, which is bit shuffle, and then a split is activated in this case. And the compression level, it's 8 or 7, both are very similar, either in score and compression ratio. Are you having the same results? In case anybody has different results or want to comment things, just tell me. Now let's use some more extreme setups. For example, let's suppose that we want trade-off is 0, and this means that we want to enforce speed. So whenever speed is needed, this combination is the one that reaches the best score. And then when you are striving for compression ratio, if we put a trade-off of 1, in this case, zlib is the winner here, with using shuffle and split is activated as well. And we are seeing that we are getting one of the best compression ratios that we can see. It is interesting that Z standard, for example, here is also doing well. So almost the same compression or the same compression, but the score is a little bit less here than for zlib. The difference is quite small, but still zlib in this situation is the winner. Then let me check for compressing balance. A balance between the compression and the compression. And in this case, LZ4 is the best for achieving a good balance between compression speed and the compression speed. And also is getting a very nice compression ratio as well. Okay, anyone wants to comment something special that they have got, or we can pass to the next section.
One comment, I tried to use floating point data so hard to compress, and I've set intentionally some bits to 0. What was presented for the NetCDF stuff 2 days ago and or yesterday, and I asked for most of the time the compression ratio were below 1, which means that compressed data are found to be larger than the uncompressed one, which is unexpected. Would it be possible to append a no-op something, because LZ4 increases the size by I think 0.4% if the data are considered as not compressible? Would it be interested in Blosc to have something that does not compress in those cases?
Yeah, I mean, Blosc, if I understand correctly, the question is about reducing the overhead as much as possible when you find uncompressible data.
Yes.
Yeah. So Blosc already comes with this support. So what Blosc does is that whenever it detects that the codec doesn't compress, it refuses to use the codec, the output of the codec, the output buffer of the codec, and it just uses a literal copy of the original data.
Okay.
And on top of that, it put the header of Blosc, which is 32 bytes.
Yeah, well, that's mandatory, of course. Okay.
Yes.
But because it found, the Btune found that LZ4 with no filter, nothing at all, that just does a memcopy plus the header with one LZ4 token saying take everything and the size of the data where to take everything. So this was the overhead of LZ4, which is no more needed. So it would be interesting in Btune that it reports that data cannot be compressed at all.
Okay, yeah, that's a good point. Note taken. Anyway, if you don't mind, let me show your wishes on a electronic mail, for example. Let us know, and we will try to address that as soon as possible. But that's a good point. Thanks for bringing it.
Yeah, so I guess you have like a hard-coded table of algorithms that you try depending on the trade-off?
Yeah.
Okay. Yeah. So you try LZ4 like when the trade-off is close to 0, and then the standard and the lib the other way around?
That's correct.
So, yeah. Okay.
In the next section, we will see how we can use we can train a neural network model for datasets, and for that we are using like exact measurements for all the codecs for most of the codecs for all the different trade-offs. So it's much more comprehensive tool for doing optimization. Okay, I think now it's time to move. Let's go with the second part of the tutorial. And for that, we are going to need the Btune training package, which is the package that is in charge of doing the training for the datasets. And for doing that, you just click here, and you will need a password for download that, because this is our training package that is included in one of the products. Let me check. Where is the password? So the password needed that you need is this one. You will see that this zip file here, you just click on it and it will download locally. It is a directory. When you unzip it, this this zip file has different wheels, right? So you need to choose manually the one that you need. Let's suppose that you have CPython 3.11 and you have, for example, a Linux machine. So you will need either this one for Arch 64 or for Intel, you choose this one. Many Linux x86 64. So when you unpack and select the one that you want, just so for example, I am on Linux, on Intel. This is an Intel machine, so I'm going to try this one. Oops. And I say pip install is not a supported wheel. Why? Because I am in 3.10, sorry. I forgot that. Okay. So now I am done installing Btune training. I hope you won't have problems on that. Just report the problems in the chat, please. So now that we have the wheel installed, we need to install also the requirements. So let's go back to the root of the tutorial and let's install the requirements. So we are in the root here now, and then let's see which are the requirements. So it's Keras. We are using Keras mainly for doing the training, Matplotlib, Pandas, and TensorFlow, which is behind Keras. Keras is a high-level interface for TensorFlow. And of course, we need Blosc2 as well. So let's install all the requisites. It's going to take a while because especially TensorFlow is a big package. Yeah, it's already done. I will wait a couple of minutes until you get into this stage of having everything installed. And then we will proceed by generating a new array, which is larger than the one that we have been trying for genetic training. And the reason for, well, just I want you to give too much information, but for training we need much more, I mean, a larger data set, because we need typically a minimum of chunks in order for the training to work well. And this number of chunks, we came up with a figure of 3,000. Around 3,000 is the minimum, recommended minimum for a good training of the model for the neural network.
Hi, Francesc. I'm just not sure. What do we? So we're training the data. I'm not sure what we're doing. We're training data. We're training the algorithms on randomly generated data.
Yes. Well, it is not exactly randomly generated data. It is, as I said, it is random, but it's between two limits, right? And these two limits are essentially filling the two first bytes of an integer of 8 bytes. So essentially we have like 4 or 6 positions with zeros, and that this is responsible for achieving almost a factor of 5 in compression ratio.
Yeah,
Makes
but
sense?
would it is the result usable on other data sets, or you know, like?
No. It's especially meant for that. So whenever you are training, you are training for a specific data set or a set of data sets. You can have models on a set of data sets. I mean, the training is very dependent. As you know, the compression process is very dependent on your data. And the important thing that is doing Btune is that you are training specifically for your data sets. So in general, what we detected is best to have like different models. The same model for the same kind of data sets. So different models for different kinds of data sets, right? Although if you want more broader training, you can also include, I mean, we wouldn't recommend to train for more than 5 data sets or kinds of data sets in a row, right? It's, I mean, the best situation is to train for this specific data set with different variations. I mean, this is going to be real data. But if you want to train for other kinds of data sets, we would not recommend to put more than 5 data sets for one single model. And the best situation is to have like a model per every kind of data set. Make sense?
I'm just thinking in the case of the synchrotron, where we have over 100 techniques, and then the data noise, and it depends on the sample as well. So we can have over, you know, thousands of different configurations. Yeah, we probably have to limit ourselves to certain very large data. Yeah.
That's not easy, but I mean that's the fate of the big data. I mean, yeah. You need to, I mean, if you want to train like effectively, you need to be careful about which kind of data you are training for. But at least, as we will see, you will have this possibility to assign one model to a specific set of data sets. Maybe you can group data sets for your setup and say, well, we have 10 different kinds of data sets, and you can do 10 different trainings, and you will get 10 different models that you can use later on production. Okay, let's continue, and you will see how that works. So now let's go to the inference directory, and let's run the same script, but with -t flag. And if flag means that we are going to create a larger data set because we need more data. So this is the one that we are using for training, and we have been using this for inference. And this fulfills the requirements to have at least 3,000 chunks. And now let's go to the training directory. And here we will see a couple of scripts. One for gathering the data. So gather data, it's where it's the first step for training. Is where Btune is gathering information about the time that it takes to compress, decompress, and also for the entropy, which is a kind of a measure that we do internally in Btune. It's kind of a measure of the estimated compression ratio that you can get. So based on these three measurements, we can do Btune can do the training later on. But this is going to be a quite intensive time. It's quite time intensive, and this will require probably, depending on your laptop or your machine, can require a period between 5 or would say 15 minutes. I don't think even if the laptop is slow, I think with 15 minutes would be enough, maybe 20. So what I am suggesting is that everyone runs the gather process or triggers the gather process. I am going to do that. So now you see that it is gathering data. So depending on the chunk, it is gathering the different. I'm going to stop that. Oops, difficult. But yeah, but you can see that yeah, different measurements are done for all the 3,000 for all the combinations. So this is going to take, as I said, between 5 or 20 minutes maximum, depending on how fast is your machine. So I would say this is the right time for doing a break, maybe a 30 minutes break or maybe 25 minutes. And after we come back, we can start using all these measurements, and we will do the actual training, and we will generate the models for our neural network.
Hi, Francesc.
Yeah.
I have one question. Both for the previous mode and this mode, how does it deal with other software running on the platform to have the timing of the task?
Yeah, that's an important thing that I didn't mention. But if you are training, better. But it is the only process that is taking the CPU in this machine. Because if there are other processes running on it, right, you will get wrong results in the sense that timings are not correct. So I mean, whenever you are training, especially during gathering, I mean, training itself or producing the models is not important, but for doing the gathering of the data, it's best to use an empty machine for doing that. That's a good point. Thank you.
Any other questions? No? Okay, then yeah, let's take a break. We'll come back in 25 minutes. Yeah, thank you.
Okay, see you later. Bye-bye.
Yep, see you later.
So welcome back, everybody. So, well, I hope that most of you already finished, or your laptops already finished the gathering process. So let me show you what my computer has gathered. I suppose you have done the same. But anyway, for example, here is the the typical lines that are output when the gathering process is running. So here we have an estimation of the compression ratio, compression speed, and the compression speed. Everything in bytes per second.
Francesc, are you sharing your screen?
Oh, sorry, I am not. Sorry. So yes, I was just describing the kind of data that the gathering process is collecting. So this, if everything went well, the output has been stored here in this directory. So typically, measurements are stored in the same directory where the dataset is, but with an extension which is called .mesh for measurement. And here you will see a lot of different CSV files with the different measurements for the different combinations of codecs and filters. So let's see, for example, one of them. So yeah, nothing new, just an estimation of the compression ratio, compression speed, the compression speed, and number of chunks. And this is essentially what the training process will be using. So let's have a look at the training script that is actually training with that data, the neural network model. So it takes 3 different arguments. The second argument is if it is a C, it is training for compressing. If it is a D, it's training for the compression. And then for the third argument or more, you can specify different arguments, right? Or different directories where the measurements are. So typically, for training for one single data set, you can do that like this. Here we are training for compression, but instead of here, it's where the root directory is for all the measurements, but you can add here an unlimited number of measurements in case you want to train for different data sets. So as I said before, I strongly recommend to do one training for a kind of data set, but you can train for different for any number. Of course, if the data sets are not very correlated among them, the training will be much worse because I mean it's the neural network model will not be able to inference the correct codecs because you are essentially pulling it, right? Marta, do you remember if there is a limitation on the number of measurements that we can fit with the training process?
No, I don't.
You don't remember? Okay, but I don't think there is a limit. We already tried with 5 at least, no? And that works.
Yeah.
Anyway, yeah, we are going to do that for the one that we have gathered the information. So let's do that. You can also do that in your laptops. In this case, TensorFlow is hitting, is getting up. Takes a while. It's a big chunk of software. And here we see that the neural network is going to be trained for these trade-offs from 0 to 1, 10 different or 11 different trade-offs. Now it is parsing all the different CSV files using pandas, and then the process is feeding that to the neural network. Now it is, I mean, the learning process is starting now. It's starting the fitting process. Typically with 20 epochs would be more than enough. And then you can see here a plot where you can see the accuracy of the training. So in general, that means that the training has went very well. so the accuracy is more than 0.95, which is very good. And we can see that the validation or loss is also quite good and quite stable. So that means that everything went well. And now, for testing purposes, it is testing with the test data. As you know, part of the data that we gathered is meant for training, and part of the data is meant for testing. And in this case, for testing, we can see that these are, I mean, the number on the left is the trade-off, and it is the first most predicted codec here, and then the second most predicted and the third most predicted. Most of the cases, the neural network only predicts one, because it is quite sure that it is going to be the best for this trade-off. But sometimes it can predict several. So in this case, it's only when trade-off is 0.5 where the model is a little bit unsure which one of these combinations is best, right? So in this case, it is between shuffle by delta and bit shuffle, non-split. And then when you want extreme compression, the neural network is predicting Z standard, bit shuffle, no split, and compression level 9, as most of us would expect. So let me explain a little bit what this by delta is, because I haven't introduced yet. I already introduced that in some talks for the LIPS collaboration, but let me say a few words about by delta. So by delta, it's a new filter that we introduced recently, based on the work of Aras Plankivicius, and he was collaborating with us in integrating with Blosc2. So thanks for his help on that. And the idea under the hood is that by delta adds a new transformation after the shuffle happens. So after shuffle happens, what by delta does is that it computes the delta byte by byte. So in this case, it uses this buffer here, 3, 4, 5, and it applies the delta here, right? And as a result, typically this can compress better in some situations. So for example, this is how this works in Blosc2. So Blosc2 has also its own I/O pipeline, and I mean the filter pipeline it can use up to 6 different filters, and all the different buffers here are reused very carefully in order to avoid copies. As you know, avoiding memory copies is capital in order to reach good performance. So the Blosc2 filter pipeline allows different filters. In this case, filter 1 is shuffle, and then by delta it's applied after shuffle, right? So although they are different filters, by delta is meant to be used always after shuffle. Eventually, you can, or optionally, you can also use another filter that you want to use it, right? But this is just to show you how by delta is working internally, and we tested with ERA 5 datasets, which comes from atmospheric reanalysis of the global climate. So we tested on 5 different ERA 5 datasets. So wind, the snow, color map, temperature, different datasets, and these are the results. As you can see, here is Blosc is not using any filter at all with this lila or blue color, but in lila we can see the violet. We can see the by delta plus shuffle in action, and you can see that the median here is the best for all these datasets. So in our experience, ByDelta is producing, was doing a very good job. And this is why we introduced it in Btune, at least on the training part of Btune, right? And the reason why it was not shown in the genetic part is that the genetic part easily explodes in combinations. So we start to add too many filters in the genetic part, the convergence would be too slow. So we are more restricted in the genetic part, whereas on the trained part, it's just a matter of spending more time doing the gathering process, right? So this is why we are including ByDelta besides the regular shuffle and bit shuffle filters as well. Make sense?
Yep.
Okay. So now that we have that, let's do the training for the compression as well. We are using a D here instead of a C. I hope that you are also able to do that locally in your machines. Again, if you have troubles, just tell us in the chat. Okay, now it's fitting the model here. Here we have an overview of the result of the training. The accuracy is not that high as compression. My hunch is that the compression is much more sensible to different measurements in time, because typically it's faster than compression. And this is one of the reasons the accuracy is a little bit smaller than for compression, but it still is very good, and especially it is stable. And we can see the training loss versus validation loss is also very good. It's very stable as well. And now let's see how it predicts on the test data. And we can see here that the same table for low trade-offs, Blosc, LZ in combination with shuffle and ByDelta is the most predicted one. And then starting here, it starts to shift towards bit shuffle, towards bit shuffle. And then for 0.8, 0.9, and 1.0, it sticks with Z standards. For 0.9, I mean, the neural network is a little bit undecided between these three. But yeah, I mean, the difference is that in this case, this is compression level 6, this is compression level 3, and this is compression level 9. For this trade-off, both, I mean, all these compression levels works very similar. And when you want extreme compression ratio, always compression level 9, which is the maximum in Blosc, which translates to 21 and 22 on Z standard, achieves the best compression ratio. In this case, it's not that far from the other part. In exchange, we can see that the speed for compression suffers a lot when you use compression level 9, whereas the compression speed is still pretty good for Z standard. Okay. So that has been done. Now let's see the models that we have generated. Now we have 4 different files, which is JSON files, and this is the model for TensorFlow Lite, which is the part of TensorFlow that is using Btune, the plugin, not the training part, but the inference part. And in this, and we have 2 files for compression and 2 files for decompression. One of the files is for meta information that we use internally in Btune. Let me show you how does it work. But essentially, it's the means for the seed ratio and standard deviation for that are going to be useful for in inference time or prediction time. And this is a binary file essentially, which is the serialization of the model for TensorFlow. Okay, so now that we have the model, let's create specific directory for our model in the inference directory. And we are moving that. So Andy has a question that he's not getting the same plots. So this is for compression, Andy?
I just ran the next instruction and I looked at my plot and saw it didn't look like your plot.
Yeah, it's quite similar, right? I mean, it's that means, I mean, it is not necessary that the accuracy would be like extreme, like very close to 1. It is dot 7 here. So the important thing is that with the number of epochs, this is stable, right? I mean, and accuracy doesn't improve a lot when you add more epochs. So this is just for making sure that the analysis, the training has been working well. And then this validation loss is also pretty stable. So yeah, I would say it's fine. By the way, you're running already on Windows. Congrats.
Yeah, but it's the same code and the same test data set, no?
You're asking why it's different. So this is for compression or for decompression? This training.
This was decompression.
Andy, the data is random and it's not the same computer.
No, but I mean, we have done a couple of trainings, right? One for compression and then the other for decompression. Well, which of them correspond? These plots correspond to?
This was a decompression, yeah.
Decompression, yeah. This is not that far as I am getting. No. I am getting very similar results. And in addition, we are not using seed, if I remember correctly. So we are using what's called random data, and also the training process. There is a random part inside of it because, I mean, in general, Marta maybe can add more details on that. But in general, you don't want the training process to be deterministic. You always want to add some randomness in the process in order to get better prediction. So to be prepared to real data to be different. Is that correct, Marta?
Yes, but like they said, it's a random data generated, so it doesn't have to be the same.
Exactly. Okay.
Yeah.
Now let me see how I can get rid of that. Do you know how I can get rid of this plot here? Maybe clicking again here. I am not that used to this zoom
thing.
The
red dot in Mac. The
right.
left upper.
Left upper?
More upper.
Left. Upper?
The red dot.
Yes. Yeah. I am seeing. Oh, sorry. It's a window. Okay. Thank you, Marta. Okay, good. So now that we have the models, and I think we already moved the models in the inference, yes. So let's move again to the inference directory, and let's start using these trained models with the data we have. So as you see, we have the model here, where there are these four files that are the result of the training. And now we are using a similar approach than before with environment variables, but with two differences. First one is that we are using this Btune use inference thing, right? So that means that, oh, sorry. I think what triggers the inference is that we specify this variable, environment variable, which is BtuneModels dir, which is specifying the directory that is where the model is. So as soon Btune look at this and finds this directory, it will interpret that you want to use the model in order to do predictions. And then this is used mainly for specifying that you want to do inference for all the chunks. Actually, this is equivalent to not specifying it, but I just wanted to be explicit on that. We will exercise these variables a little bit. So then we have a trade-off of 0.5, which is trying to get a trade-off between compression ratio and speed. And as always, we are using Btune trace here. So let's do that. And you see now we have a new line for every predicted codec, combination of codec, filter, and other parameters. And that means that inference has been used, right? So another way to see it is that model files has been found in this directory, and the time to load model is extremely fast, typically less than 1 millisecond, because they are very, very small files. And and yeah, it is working. And for this performance mode, which is compression, we can see that the codec that is predicted the most is LZ4, and filter is bit shuffle, and with a split, with compression level 5. And in general, we can see that all the predictions points toward that, right? Sometimes it uses also this bit shuffle, sorry, by delta filter as well, although the result is not that good. That means that, I mean, when you are using the model, nothing is perfect, right? I mean, there is always a chance that the model provides a wrong answer. But the interesting thing is that most of the times, perhaps 95% of the times, the prediction is the correct one. That's the thing. And in case it is not the best one, at least it's good enough. It is not very bad. So here we are getting this 4.5 times compression ratio, but the score, for example, is a bit larger. Here we are buying a little bit of a speed at the expense of getting a little bit less compression ratio. So that means also that the model or the prediction is on the verge of using one or the other. So for example, if instead of this trade-off, we use a trade-off which is more clear, probably the predictions are much more uniform, because the neural network knows better that you prefer a speed, and it's always predicting LZ4 in combination of by delta for all the chunks, right? And when we want to enforce compression ratio, it's always predicting always the same, which is set a standard, with bit shuffle and compression level 9. Make sense? Are you getting the same results? Okay, I will take that as a yes. So yeah, we are doing that. And what I am suggesting for the next exercise is to experiment with different parameters in compression performance mode. So we already did for 0.1, and I just want you to experiment with 0.0 or 0.8, and you can see the different variations on predictions. And if you have questions, just tell me, and we will have a chat. Okay, let's use 5 minutes for this exercise. It is important that you pay attention on the different predictions that is doing the model. And also, as a part of this exercise, you can use this Btune using inference to a different value than -1. So for example, you can use 3. And this is a special mode where we can mix the inference mode for the first three chunks, and after that, the genetic algorithm takes over and start. Well, it's not the genetic one; it's what we call internally tweaking. So what happens here is that for the first 3 chunks, there is an inference happening. And then for the winner, the tweaking inside of Btune is a start to tweak different parameters of the compression. It is not touching the actual codec and filter, but it's like trying different compression levels, for example. You see here, like it's trying different compression levels. It's trying different split modes here, just in case one split mode works better than another. And yeah, that is what's happening. So sometimes, I mean, you want this mixed mode, in the sense that you like to do inference for the 3 first, just to make sure that it's always predicting the same thing, and then the tweaking mode is able to maybe to reach better speed. Let's see if we have a shift better speed. So for example, yeah, this is in tweaking mode, and this has been the winner, right? In the sense that it combines the best compression ratio here, or one of the best, and then the speed is also very good. So this time is quite low, this metric, the score. But this, in my opinion, this is also an interesting way to run Btune in this mixed mode. Take your time. To experiment. And yeah, Zenek is asking a question about that the predictions are not fully deterministic. And this is essential in this kind of predictions. I mean, there is never a certainty that you are using the best parameters. There's always an uncertainty. So depending on the machine, on the measurements that is doing the Btune internally in inference time, you can get different results. That's completely normal. But again, the thing is that most of the time your results would be near optimal. That's the thing. So here, for example, I am using a trade-off of .8, for example. We can see that LZ4 is still preferred, but the compression ratio increased quite significantly. And this is because the neural network predicted bit shuffle instead of shuffle. Because with bit shuffle, generally you get better compression ratios at the expense of speed. For extreme, when you want extreme compression ratio, the best combination predicted is Z standard in combination with bit shuffle. Actually, this is the line that is the winner. So yeah, it is curious because most of the times our experience is that the split flag is beneficial when you are doing compression. It's a little bit anti-intuitive because split mode means that you are passing a smaller buffer into the codec. So for example, for a type size which is 8 bytes, you are passing 8 times less data into the codec, and you are passing this 8 times more, but with 8 times less data. And even with that, the codec behaves better, can compress better, and especially faster. Being faster is normal because it is compressing less, and probably this bit fits better, for example, in L1 cache in the CPUs. And this is probably one of the reasons why a split is beneficial. And the nice thing about Blosc, about Btune, is that it can check automatically which is the right combination for the split. Here in Tuking mode, we can see that compression level is also changed here. Any question about this mixing mode between inference and tweaking? Makes sense to all of you?
Yeah.
Mm-hmm. Okay, so in a couple of minutes, we will start the next exercise, which will be, oh,
But,
sorry, we already did.
Francesc,
Yeah.
I have the impression it's really tweaking. I mean, it's not making a factor 2 improvement or that. It's very small improvements.
It's very small, yes. And this is why it is called tweaking. It is just in case sometimes, for example, using or disabling a split, sorry, can get better performance. But in general, this is not the case. One of the things that the models have is that we are not checking for this split mode. So typically, what we do for training is to train with a split mode activated, which is because we are getting the best results that way. But in tweaking mode, it is always nice to check if disabling the split would get better performance or better compression ratio. I mean, in compressing, you never know. It's every data set is a world on itself, and every codec. And when you start to combine everything together, it's very difficult to predict which is the right combination. So this is why I like this tweaking thing. But you can disable tweaking by specifying -1. And in that case, we'll always do the inference. It's up to you. The clever thing to do is to experiment by yourself with some real data sets and get a feeling on what's the correct one. And then you normally you can use Btune for enlightening yourself on the most or the codecs and filters that fit best for you. Or if you trust it, you can still use in production. You can use it both ways, just to discover new optimization paths for you, and then set that in Blosc2 as Blosc2 parameters, or just leave the neural network to decide which is the best combination. And yeah, Zenek is saying that sometimes there is a W, it's a winner, but there is no change in codec filter. Yeah, and this is why. This is because typically all these scores are like evaluated on the fly, right? I mean, this is something that depends on the machine. So depending on the state of the machine, maybe sometimes you get a winner. But for example, here, this is the last line of winner, and we see this is the best compression ratio here, and this is the score, which is pretty low. But you are right. I mean, we have, our internal algorithm for deciding the winner is a little bit complex, in the sense that sometimes even if you achieve a little bit more of speed, it is not worth to lose some compression ratio. So we have like a little. Let me show you. Maybe it's not that. Do you remember which is the name of the function, Marta, that evaluates the winner?
You have to look it.
Okay. I think. this one. So this is the function that is declaring a winner or not. So as you see, depending on the trade-off, I mean, the logic is a little bit complex. It is the result of many experiments that we did internally. And we did that in order to ensure that winner is not changing too much with too much frequency, right? So, but I agree that it's a little bit complex to understand. So maybe in the future we can relax and do a more simple algorithm for declaring the winner. Okay. Okay, good. Now, well, we mostly have done the exercise. The exercise 3 is combining inference and 2G mode. So I hope that you already have seen how the parameters are tested now and which is the new pattern where you can see how the different parameters are changed and how predictions differ from doing a complete inference. Now we have been using the training neural network for compression. Now let's do the same thing for the compression. For doing that, it's just a matter of changing the performance mode here. So let's do that. Let's do a trade-off between speed and compression ratio. And then for the compression, this is a mixed thing. Let's enforce inference always. Okay. So in this case, it is predicting Blosc LZ, mainly in combination with bit shuffle. Sometimes it uses ByDelta as well, in combination with shuffle. ByDelta gets a little bit less compression ratio, but in exchange, well, in this case, yeah, the score is not that much. Probably, I mean, the first chunk is always difficult to assess because there is initialization times, and typically you should trust better starting on the second chunk, where initialization times or caches are already warm and gives you better, more trusty measurements. But most of the times, the neural network predicts Blosc LZ in combination with bit shuffle. And let's use the tweaking mode here. Specify 4 in this case. So still insisting here in using 35 is ByDelta in combination with shuffle. And probably is predicting that because in general, ByDelta is even if it is two filters happening in the pipeline, in the filter pipeline. In general, you can get faster speed than bit shuffle. It takes more time in general, at least for this machine. And this is the reason why it is. I mean, the predictions are oscillating between that and that. However, if we say that we want to do the trade-off more towards compression ratio, we can see that Z standard is preferred here for the even for the compression. Z standard is a very good codec. I mean, for compression can be a little bit slow, but for the compression it's still very, very fast. And remember that we are predicting for the compression speed. So it is nice that Z standard is being predicted here, although we still need that the trade-off is more like 0.8. I don't know when it will start changing. It's going to be at, I wanted to say 7.7. 7 is still predicting Blosc LZ because it is faster, but for 8, it is already predicting Z standard in combination with bit shuffle here. And the compression ratio is very close in this case. Blosc LZ in combination with bit shuffle is achieving 4.47, and Z standard is 4.52. So it's very close. When we don't worry about the speed, but more about compression ratio. Of course, again, Z standard is the, in combination with bit shuffle, is the one that is winning. As I said, this is for this data set, right? Which is essentially random data with a cut in order to produce compressible ratios. But in general, these predictions should be very dependent on your data set. But and this is why it is always nice to train the models for the kind of data sets that you are going to compress. So I will give you 5 more minutes to experiment with different parameters in the compression performance mode. And then as a final exercise, I will ask you to train models with your own data set. So if you have some data set, well, I will discuss that. But the idea is that you can read the data set and store it in Blosc2 format, which is the format that is recognized by Btune. And it would be interesting to have some discussions on your own data sets. But now just some minutes for completing the exercise on the comp performance mode. And for any questions you may have.
Mm-hmm. No, I don't know.
If you want to exchange your results with your mates, feel free to use the chat. Or if you are getting different results that I am getting, this is completely normal. I mean, I am using a Mac with 6 cores and 12 logical cores. But if you're using say a Linux with an AMD processor, you may get quite different predictions.
Mm-hmm. Maybe sort of jumping ahead to the last question, our own data sets. So in your experience, if you pick, for example, a particular NASA instrument, for example, a particular mission,
Mm-hmm.
How stable is this kind of tuning for a mission, or is that already too large in the sense that yeah, there might be seasonal effects. There might be, yeah, all kinds of other effects that sort of diminish the effectiveness of tuning.
That's a great question, indeed. So let me go back again to the presentation, because we did a lot of experiments with this ERA 5 datasets that should be similar to the NASA data that you are referring to. This is when we have been developing Btune, we use this quite intensively. So we choose 5 different things, like wind, snow, flux. So I don't remember. It's the radiation flux, precipitation, and pressure, which is typically what satellites are gathering this information. And initially, we were using we were training for all these. I mean, all of them have very different distributions. For example, on the top we see the wind distribution, and on the bottom is the snow. As you see, the distribution of data is very different. So we have experimented a lot with the combinations of 5, not only with these 2, but the 5, and creating one single model for them. And yeah, we were getting pretty good results. But if I remember correctly, Marta she will be able to correct me if I am wrong. Is that if we want very good results in general and most predictions to be correct, is to do a different model for every different kind of data set of the different distributions, right? Is that correct, Marta? That was our outcome?
Yes, there are different datasets that are similar, but we still had to split at least in 2 groups, I think.
Yes, that's another thing that you can do. That's a good point, Marta. So, for example, there may be like datasets that look similar to others, like wind and maybe I don't remember, but I remember using 2 different datasets and doing different models for these 2 sets of datasets, and that worked best. So yeah, I mean, it's in general, it's a matter of trying and getting with a good feeling on how to group these datasets. And this is why the Blosc development team, we are providing a service for customers in order to train the datasets for them. And in our study, we suggest the different ways to group the datasets together in order to produce the models for that. Is that answering your question?
Yes, thank you. And I think one of the speakers, yes, I think it was in Peter, his last name escapes me now, talk, where he said at the end that, yeah, it appears that now not only do we have to store the encoded values, but now we also have to store the model and the sampling distribution and things like that, which is of course fine. But yeah, then coming up with a standardized way of doing that is important. And
that's a good point, because if another people raise the same question, what happens when we want to train for different data sets in the same file, for example? It would be nice to store the models on every on every data set, so that when you want to open data in the future, you can still open the metadata associated for every data set and use that for doing predictions. And HDF5 is very good for that, because you can attach the different metadata for different data sets in the same file.
Yeah. And it's probably still true that when you store those 3 things, the encoded values, the model, and let's say the sampling distribution, you still come out ahead way ahead of the uncompressed data. So it's a definite win.
I would say so, yes.
Yeah.
Okay, good. So any more questions in the room or online users?
Yeah. Oh, hold on. There's a question. Hold on.
So maybe I'm jumping too far. So what is the recommendation for, like, let's try trying with our data? Yeah. How I should load them or store them?
The recommendation, well, yeah, the recommendation is to experiment. I mean, Btune is a tool that is going to help you in deciding which are the best codecs for your needs, depending on if you prefer like more compression speed or the compression speed or compression ratio, or just a trade-off among them. And then, I mean, Btune is there for helping you, right? But there is no replacement for experimentation. Btune is not going to automatically fix all your problems. You still need to be on top of that, and add your own experience, right, to what the tool is providing to you. So artificial intelligence is always like a tool. It's not the definitive answer for anything in general. The humans should always be on top of that. So yeah, I mean that's my feeling. I mean, if you have different data sets, it would be nice to come with experiment with Btune, and if you see patterns that different data sets share the same data patterns, so to say, and that Btune can generate models that works well for every set of data sets, then this is the way to go, right? Like generating maybe some models for this kind of data sets, other models for other kind of data sets, and some other models for other kind of data sets. But I mean, you have all the tooling, you have the training, so the training parts, so you can do that by yourself. I mean, I am just teaching you today how to do that, but you will be free to explore on your own.
Other questions? No? Sounds
okay.
like no other questions here. Oh yeah, maybe there's something in the chat. Oh yeah, I think Stenek had a follow-up.
Okay. If I just modify the script with bricks somewhere along my data. Yeah, about how large it should be. It's I mean the figure that I mentioned before. It's about, I mean, for having like good predictions, it's always nice to have like a good number. So 3,000 is the number that we feel it's 2,000 chunks is the number that we feel that it's okay. If you want to be more precise, maybe you can go to 10,000. But yeah, 3,000 is in general enough for do the training. Okay, so as a final, if there are no more questions, as a final exercise, I think it will be nice if you can use the same rand-int script that we have been using for generating our data sets, and then use a copy to another file, for example, or just modify it if you want to. And then maybe you can load your own data and as an array, and you can pass the array to Blosc in order to store it. And the exercise is just to explore how Btune works on your own data sets. So, I mean, for the requirement, as I said before, is that the data should be at least 3,000 chunks. You can always do your chunks smaller if your data doesn't have, it's not that large. So yeah, we will be around in case you have questions on your data. We will be happy to discuss in case you get some results.
There is a sudden exodus here. People are running for the exit, not because there's a fire, but they have to catch flights.
Oh, okay. Totally
there are
understood.
5 people here in the room.
Yeah, no problem.
Left, yeah.
Actually, this is totally optional exercise, and yeah, I hope that I have been able to explain the basics, at least, of the of Btune.
No, I think it was fantastic. I certainly learned a lot, and
glad to hear that. Yeah, Zenek is saying that it will take some time for getting the data. Sorry about that. I should have advertised that it will be nice if you can come with your own data sets. Probably I didn't advertise that enough. But I don't know. Maybe you can change the random thing and use another distribution like line space, or I don't know, whatever NumPy function you want to change the data and see how predictions are changing.
Is there, and that's sort of an unrelated question, or maybe related. We had a speaker yesterday that talked about sort of quality metrics. So when you are using lossy compression methods, she tried to emphasize the importance of the quality metrics and so forth, just as a way of also building confidence for scientists into sort of lossy methods. Do you see perhaps a chance to sort of, let's say I do a, okay, so this is all lossless compression.
It is, yes.
But do you see a way perhaps using techniques like this, like creating specific models, creating models for specific data sets to infer these quality metrics maybe?
That's an excellent question. I was there also with for the talk, and I realized that Yeah, exactly. Btune could be also a very good fit for that, in the sense that, for example, Btune, as it is now, is more about getting a good trade-off between speed and compression ratio, and testing different parameters for doing that. But of course, one of the parameters that you can optimize instead of, or you can add to that is the quality metrics, right? And then you can say, well, for me, I mean, this is the quality that I would like to reach. And absolutely, there is a lot of potential for including the quality metric inside Btune in order to find a good sweet point. And it is true that this quality thing, it's quite a problem for many scientists. I mean, my professional experience is full of comments where engineers 10 years ago, for example, were even reluctant to use compression, lossless compression for compressing their data, because they were afraid that the data would not be readable anymore, or things like that, right? And that was a gap. And now it is very, very common to store all the data compressed. And it's true that, in my opinion, the next step is to give arguments to the scientist community that, in case they need to use lossy compression, that it is not going to hurt them if you take the measure to have metrics about the quality of the data, and you have the tool for allowing you to choose the quality that you want to, right? So in that sense, we, the developers, have a lot of responsibility in the years to come to convince the scientists that they can start using lossy compression and provide the right tooling for them for doing that.
Yeah. Yeah, I think that's part of it. The tooling is critical.
It is. Yeah. And especially, convince them that lossy can be beneficial to them. I mean, if they cannot afford to store all the data that they want to, I mean, this is the best thing that they can do, right? I mean, they can say, well, I am ready to lose the data that is not important for my analysis, at least. But indeed, it's a complex problem. I mean, whenever you have lossy things, evaluating the quality, I suppose, it's an art more than a science, in the sense that part of your analysis can be affected. Depending on the analysis that you are doing, you can be more affected or not. So probably this is a collaboration between the developer and the scientist on which are the correct quality metrics to use in order to do lossy compression.
Hi, Francesc, this is Elena. I don't remember, you do not have lossy compression in Blosc, right?
Yes, we do. And this is my first talk on Tuesday. We recently introduced JPEG 2000 as a plugin, dynamic
JPEG
plugin.
2000.
Yes.
Yeah, have quick tool to analyze, for example, compressing with JPEG and with some, say, gzip, right? And giving users quick access how different data is, will be the first step.
The first step, sorry, say it again.
Just to see the difference when you decompress data, how much precision is lost, and so they can easily analyze it.
Yes.
Yeah, that will be very helpful, and people will start using it.
Yes,
Also,
exactly.
you know, JPEG, it is for, once again, it's perceived, it's for images, right? But for example, adding like ZFP may move people because it's more for science data, for modeling data, and it may help too with more acceptance of lossy compression.
Yeah.
Oh, right, I remember this, yeah. I
Yeah.
kind of was looking at...
So for example, this new plugin supports the lossless compression and lossy compression, in the same thing, in the same package, sorry, same library. And you can see the different how is called that? Artifacts.
Right, but for example, ZFP may be, you know, another one to consider here.
Yes. No, sorry. Blosc2 comes also with support for CFP. I was not understanding the name.
Oh, I see.
Yes. It is included actually inside of. It is one of the general codecs inside of Blosc. Whereas this is dynamic,
It's
only
a
accessible.
Okay.
But CFP is inside of Blosc2, so you can use it already.
So I'm behind you on catching up. I need to catch up with Blosc. Okay.
Actually, we have a blog on that. Let me show you. We did that perhaps 1 year ago. So.
Oh, okay. Yeah, I missed it.
1 year and a half ago, and yeah, and we are showing here different compression ratios depending on the parameter that you pass to ZFP. And the different modes to work with ZFP, like fixed accuracy, fixed precision, and rate. And also we did some experiment using ZFP like a third partition, because as you know, ZFP splits the blocks in like in small cubes, like a 4x4 for 2D or 4x4x4 for 3D. And we were curious about using ZFP like a third partition inside of Blosc2, and we did some experiment, and yeah, it works pretty good in the sense that we can get access to this small cube inside of the block in Blosc2. So yeah, it was working pretty good for us.
Nice, thank you. Yeah, I will check it. Thank you.
Okay. Any other questions? No? No questions here.
No questions? Well, yeah. I have nothing. I don't have much else to say. Just wanted to thank you for your attention, and I hope that we found you find the tutorial useful for you.
Yes, and I would like to thank you for joining us here, to you and your colleagues. I think it was a great tutorial. We learned a lot about Blosc, but we also learned a lot about how to put on a good tutorial. It is recorded. That's also fantastic. Yeah, I'm sure someone will be in touch with you about consenting to the recording, or if there are things that
I've been already contacted, so we gave our approval, so that will be on the network or on the internet soon, I suppose.
Great.
Yeah.
Oh yeah, you have to sign it.
yeah. Exactly.
Yeah. Oh yeah, we have some online reactions. Yeah, Robert. Yeah. Very nice.
Great to hear. So yeah, good, and yeah, it is nice for us to show what we've been working for the. I think we started that like a couple of years ago, right, Marta? Yes, we started doing our first attempts very early, and yeah, we are happy that we are doing. We are providing a production-ready tool for doing that. There are still some things that we need to iron out, like providing a native Windows plugin for Btune, but hopefully that will come. We are in contact with the Google guys in order to to pinpoint the problems that we are having to package TensorFlow Lite. But yeah, let's hope that we will fix that rather sooner than later.
And are you considering, okay, this might be a business secret, but are you considering, I mean, I'm sure you have thought about this, to perhaps do a lot of what you are doing in software right now in hardware? I mean, with all the new capabilities coming, like the, what's that architecture, what NVIDIA just came out with, that Grace Hopper architecture, for example, where you have DPUs and all kinds of other sort of special processing capabilities that you can use to accelerate I/O, to offload subtasks, or in the compression, in the wider compression pipeline, and of course do that in a configurable and trainable manner.
Yeah.
Are you thinking in that direction?
Well, I mean, if I have to be frank, we have a lot of stuff in our plates right now with these projects. I mean, we are not like a very large team, and I mean, I am firmly convinced that the GPU or CPUs are still, I mean, if utilized correctly, they still have a lot of performance to be unleashed out of the box. So, I mean, my gut feeling is that we will continue to address this performance, or trying to look into getting more performance out of CPUs. We think that there is a lot of different algorithms that can be, for example, this bi-delta thing has been a welcome surprise. We didn't expect to have another filter that would provide better results than bitshuffle, and we were surprised that in some cases there is room for more filters. And we are trying to improve that, to improve performance, to continue enhancing Btune, and but why not? I mean, if I don't know, NVIDIA or some other corporation or community is interested in like helping us to explore things like GPUs for sending data faster to memory and decompress in the GPU side of the things to get good performance. Of course, I've been approached by many people lately talking about this, but for me, GPUs are like a complex beast. I mean, for me, CPUs are already very complex, and GPUs are still adding more complexity there. But of course, we are open to any kind of collaborations that we will be presented. Well,
yeah. Also, I mean, I was thinking in a sense also that, for example, many of the modern file systems, they do compression as part of the file system configuration. And I don't know how modular they are in the sense what the user level abilities are to configure that, or if it's just standard compression methods and they say, we locked that down and you can't really change that. But it's sort of, where do you sit, what are the possible locations for Blosc if you could situate it sort of lower in the stack where the user doesn't have to think about it, but but still get the benefit.
Yeah, so this is a thing that we put a lot of thought actually. I mean, when people are giving support for compression inside of the file system, typically they cannot leverage things like the number of bytes of the item, and this is critical for getting shuffle or bit shuffle, getting good results, right? So what these compressors are missing is meta information about the data that is going to be stored, and as all of us know, this is very critical. This is very important in order to get best performance and also best compression ratios. So I don't think, I mean, trying to convey all this information to the compressors in the file systems, in my opinion, is going to be very difficult, I would say, right? Because I don't see any standard way to convey all this meta information about the item sizes or the block sizes or other parameters that are critical in order to get good performance. In that regard, using Blosc in this scenario, I don't think it makes a lot of sense. However, having said that, I do see a good opportunity, not for file systems, but for memory containers. So sometimes file systems are not, the performance of the file system is not good enough for storing all the data, as the Detrix people were showing us on Tuesday. So normally you want to store things in memory, right? And in that situation, I actually see a lot of potential in Blosc2 to become like a nice transient format to store data in memory and be able to share this data with different processes, right? So that these processes can access the data in memory in a compressed state, and they compress that only when it is necessary in the CPU caches. I see a lot of potential there, more than for Blosc, at least, more than going to the file system path, because Blosc is meant for actually being very fast, and I've shown many times that it is becoming more and more common that, especially in the compression, you can bring your data faster in a compressed state from memory to the caches and decompressing the caches when you need to, and use Blosc for doing that, for decompressing that as fast as possible. And in that regard, we have plans also to add, for example, maybe some computer engines on top of Blosc2 that are able to do this decompression chunk by chunk or even block by block in a very efficient way, and give the possibility to do operations, or arithmetic operations, or any kind of mathematical operations in general with compressed data sets already in memory. This is a more low-hanging fruit for Blosc team right now, in my opinion.
Yeah, here's a question from John.
Hey, Francesc. Yeah, I'm curious about your thoughts on using Blosc for in-memory. For, in HSDS, we have this chunk cache, right? Currently, it's an in-memory cache of any recently accessed chunk in uncompressed form. So you're saying that Blosc is especially suited for this kind of thing? Is it because it's faster to decompress compared to other compressors?
Exactly. Especially, being used as a cache for HDF5 will be a nice use case, because HDF5 already knows the meta information that is needed in order to do the compression well, right? It knows about the item size, it knows about the chunk size, and these things can be sent to the Blosc library in order to do the compression, and then the cache could store the data compressed, right? And whenever there is a need to decompress it, you can decompress it very fast on the flight. So yeah, definitely, it's a very good use case.
And the typical operation I'm doing is getting the chunk from the chunk cache and doing a NumPy selection on that. To take advantage of your block structure, do I need to use the Blosc package?
Absolutely, absolutely. You can use we implemented the hyper selection capability, not at the Python level, but rather at the C level, right? Let me show you. We have a blog.
This is Blosc2.
This is Blosc2, yes. This is not Blosc.
And is the Python packaging for that?
It is a Python package for that, yes.
Yeah.
What I am saying is that this capability is both available from Python, but also from C, which is not that usual. So things like HPyPy or ZAR are doing that at Python level. We have done that at the C level. So essentially, with this two partition schema, we can do hyper slicing quite efficiently, as you can see here when you are reading partial slices on this ending. So ending is like a layer on top of Blosc2, but this layer has been added to Blosc2 more than 1 year ago. No, at the beginning of this year. So this is available already in. So for example, this benchmark has been done with using the Python interface for Blosc2, okay? And we compare that with ZAR and HPyPy using the Blosc2 interface. So this is speed. And yeah, you can see that you can get very good results. This is for hyper slicing, and this is for writing and reading. For example, writing is also quite good, but for example, HDF5 is better, and this is because the cost of creating the second partition it's quite a lot, right? Sorry, I was reading that wrongly. So it is ZAR, which is faster than Blosc2, and this is because ZAR is still based on Blosc1. Okay. So, but the fact of creating the second partition, which is multidimensional as well, has some overhead, right? Although you can decide to do that like linear, but still there is a small overhead, but still is faster than HPyPy in this case. And for reading the whole thing, we can still get very good performance also with Blosc, with this layer, ending layer.
Francesc, just maybe something to consider, just for interest of this benchmark. If you try to use core driver and then repeat this experiment, it's interesting to see where HDF5 will be.
I think I tried. The core driver is the one that stores things in memory. I am correct? Yeah. So yeah, actually I repeated that. We repeated that several times in memory. So this is essentially fetching the data from memory instead of this, because the operating system normally loads everything in memory, right? All the file. But I remember doing that with the core driver, and the results were very, very similar to what I am showing here. And the reason is because typically, even if this is reading from disk, when you repeat the benchmark twice or three, the benchmark or the operating system loads normally all the file in memory cache. Yes, that's correct. But if I remember correctly, I did that test as well.
Okay, thanks.
Right. Great. Well, we are running way over time, but thank you. Very, very instructive.
Thanks, all of you. It has been a very, very interesting session. We have been combining tutorial with very nice discussion. So I enjoyed a lot. And also thanks to my colleagues, Marta and Ivan. It's always nice to have people helping you in the back. Yeah, hope to see you soon.
Yes.
Bye-bye.
All right. Thank you. Bye.